years later. I know Jim was maybe traumatized from that time. Okay, so, and when I arrived also, Rick Keller was the new director of ITAMP, and of course, Kate and Alex and Hussein were here. So let's go ahead and get started. We have 3 talks. I'll try to keep us on schedule to make it in time for lunch. And our first speaker is, oh yeah, there is a problem in the printed schedule.
Oh, my name is not on there. That's
Yeah, your name is not there. But it's also a problem in the printed schedule, if you looked at it. We're going to start with Rivka Bekenstein, staying with the schedule. It's online. Okay. So,
Thank you very much. Yeah, I'm sorry my name is not there. That's a mistake, of course. So I will talk today about experimental demonstrations of post-Newtonian gravity. And first I would like to thank, of course. Yeah, I think it's on. Can you hear me? No? Not sure. Let's try. Is this better? Yeah. Okay, so first, of course, thank you, Hussein, and everybody that organized this amazing symposium. It's really nice to be reminded of what a nice scientific environment we had during our time at ITAMP here. So I will talk mainly about an experiment simulating post-Newtonian gravity. And this is mainly because when I started at Hebrew University, about 2.5 years ago, I didn't have my main lab yet, so I'm also doing experiments. So I had to wait it with my quantum optic experiment, which I will mention toward the end of the talk. And I started with something that I was curious about for many years. How can we simulate approximate GR together with some quantum mechanics? And this is this post-Newtonian Schrodinger model. So during the end of the talk, I will have a few slides describing our ongoing effort towards these experiments, which is already built up, but the first results are still not yet there. Okay, so let's start with a very basic introduction to general relativity. We know from Einstein that the idea of GR that we have curved space instead of just gravity interactions. And the curvature of a space is described by the metric, which is this tensor G. And this is something maybe even kid in the world knows about, because in any science museum, we have this analog of this rubber sheet where we place massive particles and they get attracted to one another because of the curvature. What is maybe a bit less known about GR is that there is something nonlinear in general relativity, and this is the fact that masses curve the space-time. Okay, so this is why we have curvature to begin with. They also travel around the space-time affected by their own curvature, and in this sense, we have something nonlinear, very basic nonlinear in GR. So in Einstein words, which of course explain this better than me, the geometrical behavior of bodies rather depends on gravitational fields, which in their turn are produced by matter. So basically, in 2015, during my PhD, I did the first experimental demonstration with nonlinear optics of the Newton-Schrodinger system. So what is this system all about? It takes quantum mechanics and Newtonian gravity and unifies them together using these 2 equations we're all familiar with, the Newton equation and the Schrodinger equation, where we all know that one of the biggest questions maybe in physics these days is what is quantum gravity? So we heard one talk yesterday by Igor. We have a very big question here in theory, and of course, I think there are no experiments. I think I can say that in confidence, maybe not in the near future even. So this model of Newton-Schrodinger can tell us something toward this understanding of this unknown question in physics, and what I wanted to do next, after my PhD, I did this simulation of the Newton-Schrodinger equation, is to go toward actual GR. So basically add terms and to have an approximate GR in the analog system. So this is what I'm going to talk about today mostly, and this is the first experiments that we have really nice results in the lab. So you can ask me, so I will have this slide already now, why do we want to do simulation experiments to begin with? And this is my answer to these questions after having some experience in this analog system. So first, we want to do experiments with systems that are inaccessible to experiments. So we cannot do the actual experiment. What an advantage we have when we have a tabletop experiment is that we can control the parameters. We can sometimes go to parameters regime that will never be accessible, maybe even. This means we will probably reveal new phenomena, as I will try to show you today. And then one skeptic question that you can ask is, OK, why not just calculate this using the equations? Because we do know the equations. And my answer to this is that usually or sometimes the equations are very complicated. There is some, I would say, complexity in order to do the theory. And this will just mean not that you can't do it, it's just that you're not going to reveal the phenomena if you're just going to look at the equations and simulate them. So sometimes we just reveal new things when we have an experiment. Yeah, this is weird to say this in an ITAMP symposium of everybody doing theory, but we know that sometimes results just comes out of the experiment. But we have to do this, which is find the analog system in order to manage to do this kind of experiments. And in order to simulate this self-gravity, what we need is something nonlinear, a nonlinear system. And the mapping that we found is between these massive stars, massive particles that curve the space-time, and between a laser beam, an intense laser beam that changes the refractive index in the material, and by that changes its own propagation, its own dynamics. So this is called the paraxial wave equation, the nonlinear one. It describes the evolution of a laser beam inside some nonlinear material. It's propagating in the z direction. It has some similarity to the Schrodinger equation. There is a diffraction term, and there is a nonlinear term. So this is a change of the refractive index that is happening because we have some electric field. Can you still hear me? Yeah, OK. So this is the change of refractive index delta n, and it's some functional of psi, which is the electric field amplitude. Now, if we increase the power, we're basically going to get different dynamics. For example, we can have solitons. So solitons means we have an exact balance between the diffraction term and this nonlinear attractive term. Usually in optics, what people would do is local nonlinearities like the Kerr effect, meaning that we have an electromagnetic field in a specific point in space. The refractive index is going to change exactly in that point. In order to simulate gravity, we need some long-range nonlinearity, and this is something I had to use in order to simulate this self-gravity effect. And what I used is the thermal nonlinearity. So this is already have been used in 2015 in the experiment. And the idea is that we shine a laser beam inside the material. The laser beam is slightly absorbed in the material, raising the local temperature. Then we all know by the heat equation, a Poisson-type equation, that the temperature is going to change all around. If we assume, and this is an important if, because in 2015, I assumed I have a linear relationship between the refractive index and the change of the temperature. And we're going to break this now. So I got a Poisson equation for the refractive index. And if I couple this equation to the paraxial wave equation, the nonlinear one I showed you before, we have two equations that are coupled, and they give us this nonlinear evolution of the laser beam inside the material. So the laser beam is propagating in the z direction. If we increase the power, we get different evolution. So this is a nonlinear dynamics, and these are the equations. This was 2015. So this is the paper from then. I basically managed to demonstrate known gravitational effects, but in this self-gravity nonlinear system. For example, gravitational lensing, tidal forces, etc. People in the gravity community were very happy because for maybe more than 20 years, they have been looking into these equations, and it's the first tabletop experiment where someone can actually demonstrate this. And also in the nonlinear optics community, people try to have similar experiments, and they manage to observe other gravitational effects. So this is very nice. But when I started my own group, I had the opportunity to go back and try to actually simulate general relativity. So of course, we're not going to jump from Newton to GR, to complete GR. We're going to go in a step. And this is the step we have made. There is the metric tensor, the Newtonian one, which has only this gravitational potential that enters in the temporal term. In the Weinberg book, and this is, I don't have the reference here, but this is just textbook, okay? This is Weinberg. You can see that there are many more additional terms that get into place when you actually look at the first order of approximate GR. So this is just by adding the first term of this energy. And then you can see that if we add an additional term, this is the quadratic term of the gravitational potential, we have some correction to the system. And in our experiment, we're going to basically neglect, and I can explain why after if you want, all these other terms. Okay, so we cannot really add all these terms immediately. So what we're going to do is work with really high power, high intensity of the laser beam, which will mean that we cannot assume anymore that we have a linear relationship between the refractive index and the temperature, but we have this quadratic term. Yeah, Nicole?
How high is high?
So this is more than 4 watts. Basically, you can burn your hand. I'm not talking about getting blind, but if you put your finger in the laser, you have a hole in your finger. So it's high power. Okay, it's really not nice to work with these powers, but there are higher powers in labs. You can get to 10 watts. You can get even to 20. You can get to more, but it wasn't a regime anybody worked with before. So it was usually around 1-2 watts. And then if we do that, we basically can go from Newtonian gravity to post-Newtonian gravity. That was the guess, okay? We hope this will happen, but we weren't sure yet. And then a very bright student, Omer Paz, he basically came into my office and said, I want to do a follow-up paper. I want to work on this gravity simulation. I saw the paper from 2015. which was very surprising for me. It was like a new lab. I had nothing going on. I told him, OK, try to open the Weinberg book, and let's find the analog. So this is the analog he found. We have the Schrodinger equation with some potential, V. V is basically not just the Newtonian potential anymore that fulfills this Newton equation, but it has this quadratic term. It's important to understand that phi is negative in gravity, meaning that these two terms have opposite signs. So instead of really focusing as before, we have actually some defocusing effect, which will mean that in the refractive index in the material, we will need to have the regular thing we had before, but also some quadratic term of the temperature. So the guess is, if we go to high powers, maybe we manage to see this. Maybe we have the right sign of gamma 2, which will be negative, in order to simulate the approximate GR. So this is the post-Newtonian equations. And the first thing we did is find the soliton solution. So this can be done numerically, but it's really nice. It's time-consuming. Okay, for each point of this graph, which is called the existence curve of a soliton, you need to solve a new simulation with new initial conditions. It's just time-consuming. You need to use all kinds of tricks. It can take hours on a regular computer. So this is basically the soliton existence curve. This is something known in nonlinear optics. You have the width of the soliton as a function of the power. So each one of these points is a self-consistent solution to the nonlinear set of equations. And you can see that we have two different solutions, one for the Newtonian gravity and one for the post-Newtonian gravity, which is obviously a bit different. And at some point, we cannot anymore get convergence of the solution in theory. Okay? We didn't manage. I'm not saying it's impossible. We didn't manage to do that. So this is the experiment. It's a very simple experiment. This is not called Atom's experiment. This is an experiment that a single student can build in the lab, not in so much time. He just needs to really align the optics well, and that's enough. So we have a telescope system, and we have a lens that focuses the beam inside this nonlinear material, which is SF11. And then we have the input beam and the output beam that we image. And this is typical results of the experiments. We shine a laser beam, and we can see that it's focused inside the sample. We increase the power as the experiment goes. Now, this, in theory, would be not so nice to do. Okay? We need to do the simulation and then increase the power each time in completely different simulation. In the experiment, we just tune the power of the laser. So we have a focusing. Then at some point, we have something that looks a bit stable, which we interpret as the Newtonian soliton that we are familiar with. We keep going, and at some power levels that we've never seen before, we see another something that looks like a soliton. We are going to interpret this as the post-Newtonian soliton. Then we have the focusing effect, which is really good for us because we wanted, instead of having focusing, a quadratic term that will give us defocusing. So this tells us that our material actually acts as we wanted it to act. OK, so then we basically take the existence curve out of the experiment now. So we do this manually. So this is why the error bars are pretty big. We look at these locations where we have stable solutions, and we extract these two different existence curves. And obviously, we have completely two different solitons in this system. One that has to do with bigger powers, and we see that the post-Newtonian solitons are wider compared to the Newtonian one. So this is very exciting for us. In nonlinear optics, when you find like 3 or 4 points of an existence curve in an experiment, that's sort of enough. It always looks like that, by the way, the trend of the graph, also in Kerr nonlinearity. But usually, they're not two different complete solitons. Sorry. At the end, we see that we get this focusing effect. And this is raw data from the experiment. So it's really nice. You can see in your camera how the beams become wider if you just increase the power. OK, so until now, everything made sense until this point of the experiment when stuff became really unclear. So my student came. So this is another student now. Her name is Shai. She said that I get this really weird beam at the output of the nonlinear material. And at the beginning, I didn't believe her, okay, because it was really weird. We expect solitons. In gravity, we expect localization. There are all kinds of things we know about. There's a lot of literature, but I've never seen anything like this. But then she repeatedly found these nice solutions, and we were sure it's something real. And this was, I would say, a nice scientific sleepless weekend when I thought about this problem. And the first time I felt like I'm needed in the research because they managed to do the theory, the simulations, the experiment. And then I actually tried to think, what is this? What is going on? So what I found is that you see you have this 2 peaks beam, you have a ring beam, you have this anisotropic ring, and we have 2 peaks and this ring around it. So completely exotic beams. So then I send the student doing the simulation to simulate and find what is the refractive index for very high power. He never got convergence of the self-consistent solution, but he can just calculate the refractive index. And he found this refractive index which makes a lot of sense. So you should think about minus the gravitational potential. This is why it's positive. The refractive index is positive. This is an attractive refractive index, attractive potential. But in the center, where we have really high intensity, we get something which is defocusing, repulsive. So you can think of it also as an opposite Mexican hat, which is known in physics. So then you can just look into the literature and see there are linear modes of this Mexican hat potential, which look like that. There is a ring solution. There is a mode that has these two different peaks. And there is even two peaks and a ring around it. So there is really some similarity between these linear modes and this nonlinear evolution we see. So we went back to the simulations, to the theory, and we managed to see two of the beams that we saw in the experiment, not all of them. We managed to see this evolution into a ring. So a Gaussian beam, a soliton, at some point defocuses and becomes a ring. And we managed to see this anisotropic ring. And this is basically where we're going to stop to talk about this project. But my main takeout from here is that sometimes you do the experiments, you find these really things you never expected before. And these beams is a result of this additional term of the defocusing effect, meaning that definitely we have a post-Newtonian simulation of gravity. So this is this project. And now I'm going to talk about our efforts toward solid-state-based quantum metasurfaces. I think I have exactly enough time, even for a lot of questions. OK, so what is the main idea? Usually in conventional quantum optics, we want to enhance the interaction between atoms and photons to do all kinds of quantum gates, for example. For that, many times, we will structure a nanophotonic structure, a waveguide, a cavity that will help us to increase the interaction. We are going in a different direction, and this is using this idea of quantum metasurfaces. There is a sub-wavelength array of atoms, or quantum emitters. And by controlling the spin of one of these emitters, we're going to affect the quantum response of this full array to light. So if we send a photon, depending on the state of the spin, it's going to be reflected or transmitted. Now, this system is potentially scalable in the sense that we don't need many cavities, many waveguides. We just need arrays of atoms. But they need to be sub-wavelengths. So this is related to the symposium, ITAMP Symposium. So this theory work was done here when I was an ITAMP postdoc, collaboration with three, I would say, former ITAMP postdoc, which is Igor, Hannes, and Misha, also an ITAMP postdoc. So we're all working on this together, and this is the theory. We assumed atoms at the time, and we assumed that we can excite to Rydberg, highly excited Rydberg states. And by that, we can basically blockade the atoms and the light. Then we can have a superposition state of a ground state and a Rydberg state, and we can have transmission or reflection, depending if we have an EIT condition or if we ruin it by the Rydberg excitation. That was the basic concept of the theory at the time. And what I'm trying to do now in my group, a lot of follow-up since then, in theory and in experiment. In experiment, I think the group, which is the only group probably that saw this until now, was the Immanuel Bloch group in Munich, or in Max Planck. They managed to basically see some coherence between the state of an ancillary atom, which is in the Rydberg state, or in a superposition of G and R, and the reflection of light. So this is this paper. And actually, me and Suzanne wrote a nice review on that, News and Views. And then there's a lot of theory going on in the field. So this is Ignacio's group, Suzanne's group, I can't even, so many groups working on this. So this is a sub-wavelength atomic array, trying to do all kinds of quantum information, looking at different geometries, nonlinearities, and a lot of other things. OK, so what we are trying to do is basically do this in a solid-state system. So this is now a completely different platform, not atoms anymore, but actually defects in a solid. And the idea is that we want to employ the spin degrees of freedom of these quantum emitters that are called silicon vacancy centers. And we're going to do this using a symmetry-based considerations. So now we don't have the Rydberg excitation anymore. We don't have the access to this Rydberg state so easily. So we need to think of different mechanisms of how to control the response to light. If we want to actually have scalability in this system, which is not trivial at all, we need to have these atom-photon gates that we already have from the 2020 paper, from the theory work. We need to have atom-atom gates, which is something we are developing. We have some results, but only if we have time for questions, I will mention it. And we want to do it in a solid-state-based system that we can basically have a chip where we can have many, many quantum metasurfaces on it. OK, so the platform is silicon vacancy centers in diamond. So after I actually finished my ITAMP position here, I also worked in a lab in Misha's group doing silicon vacancy centers. I already have this idea that I want to do experiment with these quantum emitters. And we managed to see emission of single photons out of the single SIV inside a nanophotonic cavity. So here you see the G2 of this type of experiment. Basically, they're nice quantum emitters. They have long quantum memory. They have good interactions with light. And we can control the spin degrees of freedom. And we also managed to see emission of streams of photons from this single SIV. So this is an experiment of 24 hours, which basically tells us that we have an efficiency of 15%. So if we do an experiment, we have 15% to actually get a single photon out of this emitter. So this sort of convinced me that this SIV is a good emitter to work with. And this is why we base our experiments on that. So if we use SIV and we want to use the spin degree of freedom, first we need to cool down the system, because we have two ground states here, and we won't want any thermal coupling between the first one and the second one. So we need to use a dilution refrigerator, and now we understand why I couldn't start with this experiment at the moment I landed at ITAMP University. I had to basically prepare the lab and get this dilution refrigerator. Then if we apply a magnetic field, we can have splitting of this ground state, and we can have our spin, which will be the degree of freedom that will control the response to light. Just a moment. Okay, so basically what we do is we implant silicon ions inside diamond, and by that create these defects, and we can do it in a deterministic location. It is not clear yet if it's going to be good enough or we need to improve it, but we can basically create an array of quantum emitters that will act as this quantum metasurface. And this is actually the first sample that was made here at Harvard by Eric Knall, who is a PhD student with Misha. And he prepared these holes for us, and basically then we could implant the silicon ions in a specific location within the diamond. We have some challenges, like this inhomogeneous broadening that these emitters have, and this is a really big issue. And we have some directions of how to deal with it, but this is, again, an ongoing, very risky project that we're working on. Okay, so this is how the system looks. There is a dilution refrigerator, and we have just a confocal microscope where we can scan the sample. And what we have in a sample is many, many different atom arrays. So each one of the dots you see here is a completely different quantum metasurface or atom array with different parameters that we want to study and see how the collective resonance looks like, what is the response to light. And at the moment, this is the situation of my lab, so everything is set up. We have some nice resolution. And for the first time in the last months, we managed to see some fluorescence out of this sample, but it wasn't from the atomic arrays, but from some other markers we have inside, so it's not yet the actual experiment happening. We are almost there. And I hope the next time, the next symposium, I have many results to show in this system, hopefully. So with this, I would like to summarize. We managed to see this post-Newtonian gravity with Schrodinger equation. And this is really nice experiments and a nice, basically, tabletop system that we can now try to see all kinds of gravitational effects that you cannot see in Newtonian physics, like frame dragging, boson star formation, and other things. And then we're also working toward this more complicated, I would say, experiment that will take us more time, which is realizing these quantum metasurfaces in a solid state-based system with silicon vacancy centers in diamond toward the direction of doing some quantum information with these kind of systems. So with this, I will acknowledge my young group at ITAMP University. So the experiment I was talking about at the beginning, the theory was done by Omer Paz, but then Shai actually built the experimental system and took all the results you've seen, these really nice results, and Jonathan have done the soliton solutions of the nonlinear equations. So this was a collaboration between 3 different students, and this is the dilution refrigerator that we installed in September 2023. So this is really fresh. And the fact that the experiment is actually showing something, it's very exciting. With this, I would like to thank you. Open for questions.
Very nice. Any questions? Yes.
So in these nonlinear systems, could you send 2 laser beams and you see that they attract each other and see like 2-body bound states like?
You can send 2 solitons to this nonlinear system. You can see them become attracted to one another. You can also send 2 different, and this was done, by the way. You can also send 2 solitons with some angular momentum and see some rotating stars, for example. Yeah, you can show all kinds of nice things. You are limited to 2-dimensional GR because the z direction is time in the Schrodinger equation. So this is one limitation. And for now, we got these two terms of the approximate GR, so we still have work to do.
So can you say a bit more about like for atoms, there are pretty stringent requirement, or like a great advantage of the atomic system is that they're so homogeneous. With the vacancies for like to see some cooperative effects. Like, can you comment on like homogeneities and spatial placement, but in particular
it's a very
frequency?
serious problem. So we have two approaches of how to deal with it at the moment, and we may have others. One is actually more statistically. So instead of implanting one ion in each one of the sites, the first sample we just decided to implant, and we calculated exactly how much we need, but we sort of implanted tens of ions. And the idea is that statistically, you're going to have one ion talking to one SIV talking to one SIV here, to one here, to one here, and you will have this nice array, but you will have also many that you're not going to talk to this coherence interaction. So this is our first, this was like the way we decided to start. Then you can deal with like the way you prepare the sample. So we anneal to very high temperatures, for example, and we do some process where we implant the ions. You can change it a bit the way you're doing this and improve the homogeneity, basically, of the system. So this is another way to go. But it's a serious problem. If there is some reason this is not going to work, it might be the reason.
I think you can count somewhere in the ballpark of the line width of the system so that it becomes proper.
Yeah.
Thanks. So as far as I know, there's kind of some question of whether gravity combined with quantum theory is like mean field, where if I'm in a superposition between two positions, I feel like the average of the two, or whether it would kind of attract to one or the other and I get entanglement. Does your experiment kind of say anything about that, or you have to choose one of the two, and which one is it?
Yeah, so in my experiment, it's like semi-classical gravity, so it would be the average between the two. It's the only thing I know how to do now in the experimental system, but of course, in theory, you can do whatever you want.
We have time for another question.
Maybe just to kind of like get a sense, you showed that if you shine a very big laser light, instead of seeing just a single body, the gravity seems to split. What is the gravitational analog to this phenomena? It seems like we tend to see the clumping of matter.
That it's split, you mean? Yes. The fact that it's split? So I think I'm going to answer with an example. So at the moment when we saw that this post-Newtonian approximate GR has this opposite sign, it was very non-intuitive for me, because if we go from Newtonian to GR, I expect to have a stronger gravity. But I think it's when you have a sum and you try to approximate anything in physics, you always get many times you get opposite signs, right? It's sort of like the first guess would be a linear, something, and then it's going to actually come down. So I think it's the same thing. The only reason we get this defocusing is because we have the second term that is dominant now. And it means, and if we look at Schwarz, so I was concerned about this, so I went to Schwarzschild, which is the black holes metric, and I checked what's going on there, and it's exactly this. The first term of the Newtonian gravity is just attraction. You add the second term in Schwarzschild in a black hole, and you get a defocusing. So it's exactly this, the idea that we have only two terms, I think, for now, and we don't have the full sum that gives us GR. So within this only two terms, you get this defocusing.
All right, let's take Rivka again. Okay, our next talk will be given by Misha Levensko from the Institute of Science Technology, Austria.
Yeah.